for having me here. Yes, so the talk is divided like in two parts. The first one is the clustering, and the second one is the unmixing of the multi-component analysis. And yeah, as Leonel said, this is the work that we've done here in the last 3 to 4 years with Enrico. And as he said, one of the projects kind of led into this spin-off. So it's kind of trying to commercialize part of it. Okay. So clustering methods. Clustering is a family of machine learning techniques that deals with solving the problem of given some data, finding, attaching a label to each of the points so that they form clusters. So basically the task is to group your data automatically. The other big family of machine learning techniques is the classifiers, which is given a new point and given a set of labels like we have here. So in this case, the colors assign one of the given labels to the new point. So why clustering? Well, as you have learned earlier today, the phasor plot is this technique that we use in fluorescence imaging, both for lifetime and for spectral imaging, in which at each pixel of the image, you may have a distribution of photons, say the color of the photons or the lifetime of the photons, and that distribution maps to some position on the phasor space. So each of the thousands of pixels here has a representation on this two-dimensional space, and some distribution of points will appear in this phasor space depending on the information that you have on the original image. It makes sense then to come up with a technique to automatically select these clusters in order to then go back to the original image and see what this different information carries and so it basically segment the original image based on, in this case, lifetime information. As you see, well, in this case, it's the nuclei and the cytoplasm. Traditionally, this has been done manually, as in you grab and you kind of paint or put your cursor on top and see what area corresponds to each region you're marking on the phasor plot. So yeah, we started this technique to develop this kind of early on, I'd say just before the pandemic. And so it's a computational work, so we could do it from home. So it's based on simulated data at the beginning, and then with Belen, we prepared some samples kind of to test it, but everything was done offline at the beginning, right? So here we prepared some simulated data. This is what we call the ground truth. The ground truth is like you cook your data and you have it ready and you know exactly each of the points what cluster it belongs to. And this data was prepared drawing photons from an actual lifetime distribution. So it's like simulating actual random distributions with particular lifetimes. So for example, this is a specific lifetime component. This is a longer lifetime component. And this is a mixture of, say, I think it's this one and one that would be like on the other side of the phasor plot. And here it's combinations of some lifetime components plus a zero pole. And there's like different ways we prepared this data, basically to test different cases. Clearly, this is an easy case, clusters are isolated. We call this the skewed case. So they are kind of extended in some direction. Testing size of the clusters, testing the number of elements in each cluster. So there's a lot of points here and not very many in this one. And then a high problem in which data is crossed over. We prepared all these ground truths to test the different algorithms that are available in the literature. So you may have heard of K-means. K-means is probably the most well-known of the clustering methods. It is based on distances. So you find, given a certain random grouping, you find the mean position of all the elements in that group and then measure the distance of all the elements to that center. So you basically want to minimize the distance to the center of the group while maximizing the distance among groups. There's other techniques based on connectivity and graph theory, based on kind of local density. Well, dbScan is a well-known, which is based on density. Mean shift is a kind of a weird one where you throw a grid and then you shift the points on the grid to match the most elements in your space. And then these are more modern techniques. Spectral clustering is based on eigenvalue decomposition. And the one that I'm trying to make the case that is the best for Phasor data, which is Gaussian mixture models, is the last one in the last column. So, okay, if the data is easy, they all succeed, right? It's perfect assignment for all of them. The number up here is the Jacquard index. It's unity when all the points are well assigned, and it goes below unity when they start to mess up. So examples of failing, k-means, which is based on distances. So if you have these tails that are kind of, these points here are closer to the mean position of this cluster here than they are to the position of the mean position of the cluster, the red cluster. So here you start to see failing. Other cases in which they're failing, well, the ones that are based on density, if you have isolated points, they kind of drop off. They're assigned to an outlier group. This isn't one of the good things about these methods here, though, that they allow for outlier points in your data, whereas the traditional ones don't. You simply say, okay, if it's 3 clusters, it's 3 clusters. Well, as you see, in each case, there's different errors here and there. For example, this is a complete mess. This cluster was joined a single one, and then this single element in a cluster. And obviously, the hard one, the Jacquard index, starts to go very low. I have marked here which are the best in each case. First one, everyone succeeds, then you start to see some are better than others. But as you can see, the last column is consistently the one that outperforms the rest of the methods. And this is not by chance. There is a reason behind this, and it is that the noise in the photon distributions and that you obtain from your measurements, let it be lifetime or spectra, changes the shape randomly in all positions, which means that your data on the phasor plot tends to spread out as a Gaussian distribution. So it makes sense to try to model your data with Gaussian normal distributions. Okay, so what are Gaussian mixture models? Well, what you're doing is that you're assuming that your data can be modeled with a weighted contribution of 2-dimensional Gaussian distributions. So you have this, you want to model your data as the sum of k Gaussians, and put this G sub I, each one with its weight, such that the weights of the k Gaussians adds up to unity. And each of these Gaussians, this is the general expression for a Gaussian in n dimensions, where x is each point in the n dimension, so it's a vector, and this is the covariance matrix on n dimensions. If you think of it in a 2-dimensional space, which is our case, what you have is some cloud of points, which if you were to histogram it, you would see that it has some Gaussian shape. And then what you're trying to model is this distribution on top of these points. What parameters that determine these distributions? Well, as I said, the weights of each of the Gaussians, the centroids of each of the Gaussians. So what is the vector that goes from the origin to the center of each of the Gaussians? And the covariance matrix for each of the Gaussians. This covariance carries the information of the shape of the Gaussian. So it's a standard deviation in G direction, standard deviation in the S direction. And then there's the square of each of them, the product of the two, times the correlation. So basically, there's a bunch of parameters that you need to find out for each of the Gaussians that you want to model your data. In fact, it's k weights. In this case, it's 2k numbers for the centroids, because it's one for the G direction, one for the S, and it's 2k values for the standard deviations. Literature on this, there's a bunch of it. The first hints at using Gaussian mixture models to model data is over 100 years ago by Pearson. This is the same guy that you know from the Pearson correlation. And he was applying it to biological problem as well. Then kind of the boom of the pattern recognition and machine learning techniques is in the 70s. So, and this is when the expectation maximization algorithm was published, which is the typical one that everyone uses to solve this kind of problem. And it's basically an iterative process in which you start with random positions and random values of your parameters and loop until the data doesn't change anymore. So there's like a 2-step in each iteration in which you try to shift the Gaussian depending on the distribution of your points, and you keep iterating until your parameters don't change or change by a certain threshold. So you can see this. There's still modern publications on this, because it is an open problem how to choose the number of Gaussian distributions that you want to model your data with. Here's an example of the method at work. You start with some random positions and you kind of shift the data until it seems not to change anymore. And this is your recovered cluster data, which if you compare it to the Gaussian, to the original ground truth, it is close to perfection, if not perfect. Yeah. Here's a hard case like the ones I was showing before. And as you can see, it still models the data pretty well, to the point that you even start to get that the system can tell when the data is mixed up. For example, the two red points on the left side that are beyond the middle cluster are still assigned some probability of belonging to the rightmost cluster. This is one of the nice things about this method, that for each point, you get a probability of belonging to each of the clusters. So, I mean, clearly the 2 points on the far right have 100% probability of belonging to the yellow cluster and 0 to the other two. But some of the points here in the regions in between, you get some proportion of values, which kind of allows you to maybe threshold them out if you want to be very strict with your data, or at least you have the knowledge that you are in a bit of an unknown or dodgy space. Okay, let me show you with actual data that we have taken in the lab. So this is basically this is the data that kind of triggered the whole exploring this technique. So it was a collaboration with the Zhao lab here at UCI, and Tamvu is the main collaborator. And the project was regarding labeling mRNA transcripts in cells, and now it's in tissue. We're doing this. So in this case, we have transcripts in a cell that are labeled with 2 different fluorophores, 2 different genes, 1 fluorophore for each gene. And as you can see, I mean, now it's not so clear, the clusters, but there's still maybe 2 distributions. So what you're used to seeing in Phasor data is not so much what I'm showing here. Here, if you zoom in, you have a bunch of points. Each of these points corresponds to one of the pixels in the image. Usually what you see when you, in the publications or when you're working with your data, is a heat map. So you're basically gridding this Phasor space into a histogram, counting the number of points in each square, and this gives you the Phasor distribution that you're used to seeing. But for our clustering techniques, what we want is to work with the original list of coordinates in the 2D space. As I was saying, yeah, so you have 2 genes, one tagged with Alexa 647, one tagged with Atto 647. It is 2 probes that emit in the red part of the spectrum, but have different lifetimes. Alexa has a lifetime of about 1 nanosecond, Atto 647 of about 3.5. So you'd expect the Alexa to be the cluster on the right and the Atto on the cluster on the left. You feed the data to the algorithm, and this is what you obtain. So again, 2 clear clusters, some region of maybe uncertainty. And then you can go back to the original image and successfully detect, so assign one of the 2 labels at each of the detected, well, at each pixel, and therefore at each gene. Here's another example that we kind of cooked up for the paper with Belen and Enrico. These are cells loaded with 3 different dyes, lysotracker deep red, membrane red, and lithium bromide. They all emit in the kind of red area of the spectrum, and we took a snapshot in this spectral window. So it's a single image, but there's the information of the 3 dyes in the lifetime. You look at the Phasor plot of this image, you kind of see some spread out distribution. Since we know that there's 3 components in here, we solved the clustering problem for 3 components. This is what we obtain. Go back to the original space, and we the result is exactly what we expected. Lyso tracker would be the stuff in the cytoplasm, the lysosomes. The membrane is the membrane, and the ethidium bromide is tagging the nucleoli in the nucleus. And here's a more complex problem, and again with the transcript project, we were labeling 3 mRNA targets with 2 different fluorophores. So mRNA target 1 in the top left is labeled with 1 fluorophore, mRNA target 3 with a different fluorophore, and mRNA target 2 is labeled with a combination of the 2 fluorophores. So there's exactly the same number of each of the 2. They were kind of alternated in the sequence. So the expected emission of one of the probes would be on the universal circle, the other probe on the other side of the universal circle. We know that we have 2 lifetimes. In this case, it's the same that I was showing before, 647, Alexa 647 and Atto 647. And then the genes that are tagged with exactly the same proportion of the 2 should be right in the middle, because they have for each photon that comes from one probe, you should get a photon that comes from the other probe. Obviously, you have a bunch of other fluorescent components in your sample. I mean, our biology is fluorescence. Nearly everything is fluorescent in the molecular scale. So you have a bunch of components here that are pulling your data elsewhere, but you still see the 3 main groups, which are what you expected to see. Attempt to cluster automatically, you obtain 3 clusters, and then you go back to the original space, and there you have it, the 3 genes separated. Still, you have some areas of uncertainty, as we showed before, which would correspond to the regions in between. This is actually a 3D Z stack, so I'm just showing the projection as you project down. But for example, here, these 2. This one marked here is actually 2 that are very close. So you're getting 2 transcripts that are so close that are overlapped, and then you start to see uncertainty in your data. And this goes to the second half of the talk, which is about mixing this data. Anyway, another thing that I would like to mention is that the Gaussian mixture model is very important at modeling Gaussian distributions, but not always you have Gaussian distributions on the phasor space. Sometimes you have the linear combinations. So in this example, your transcripts are either labeled with 1 component, with the other component, or with exactly 50% of the 2. But you don't have, or you shouldn't have, any pixels with, say, 25% of one probe and 75 of the other. So that's why you don't have a flat linear combination between the 2 extremes. You either have the central, or the one on the left or the one on the right. If you do have kind of a equal proportion of all the possible combinations in between, that you cannot really model with Gaussian mixtures. And unfortunately, it is a pretty common thing that you see. So here's a very complex case in which you have a bunch of distributions, and you see these streaks which correspond to exactly the transition between one component and the other. You have a bunch of pixels which have all the possible combinations between the 2. So if you try to model this data, you see this doesn't really make sense. This red cluster here, for example, is clearly wrong, or this blue one on the left. And if the proof is that if you go to the original data, the blue one on the left side is basically not a real cluster. It's just trying to model a transition between 2 separate regions. The same applies to this guy here or to that guy there. So yeah, there are some limitations in this technique. And the second main thing, and this is what I was mentioning before, that it is an open problem, how to choose the number of clusters, or what's called the overfitting problem. So for example, in this case, it is clear that we want to find 3 clusters here, because you just see that there are 3 clusters. But one could say, well, if we have, I think it's 400 points in this data here, wouldn't it be even better to model this data with exactly 400 Gaussians, 1 for each point? That would be a perfect clustering. So you say we have 400 clusters, and each cluster has only 1 element. So this is why this is called the overfitting problem. The computer cannot tell if that is a better solution or a worse solution. You need to somehow tell it, no, we are interested in lowering the number of clusters. So there's some statistical methods based on information theory, which penalize the number of clusters so that it takes into account both the model, the quality of the model and the number of clusters you're using for the model. And what in the literature people do is try to find a minimum in these criterions. So in this case, these two criterions calculated for this data here, you see some angle down here, which is telling you that 2 clusters is a bad modeling, 3 clusters is a very good model, and 4 and 5 and 6 are kind of very close. So it doesn't change much the data. So you'd say, okay, we model this with 3 clusters. But in reality, you don't get these minimums here. You kind of, what you get is an angle. That is what usually people do. Find a discontinuity in the derivative and say, okay, we choose this number of clusters. For example, here, what's the best solution? 3, maybe 6. Hard to tell. Yeah, and that's about it for this first half of the talk. Anyone has any comments on this? I didn't mention it, and I think interrupting is a good thing. If anyone has, if you want to ask questions in Spanish, that's also allowed. Okay, well, moving on to the second part. So multi-component analysis using high harmonics on the Phasor transform. You have learned this morning about the Phasor transform. I'm going to do like a quick recap. You have your list of arrival times or a list of wavelengths assigned to each photon, and you build some histogram of photons at each pixel. In this case, it's a lifetime information, so its intensity is a function of time. And this is the stimulation period, the time between 2 periods, which is usually in the megahertz. So this is nanoseconds between these 2 points. This shape, whatever shape it is, you map it to the Phasor space using these 2 equations. This may seem a bit complicated, but it's actually pretty simple. You just have your intensity as a function of time, times a sine function, or times a cosine function. So here I have an animation to try to explain this operation you're doing here. You have your decay as a function of time. It's an intensity. It's this value in here, where time is the horizontal axis. You fit a sine function such that the omega here fits exactly in your stimulation frequency period. You multiply the 2 together. You get some function. This is the product of the 2. And then you compute the integral so that you have the numerator of this equation here is the area, it's the yellow area under the curve. Normalize it over the black area and you get some number, 0.4. You repeat the process for the cosine, which is basically shifted 90 degrees, multiply the 2, sum up the area, and you get some number, 0.2. The combination of these 2, these are 2 coordinates of this specific shape on the Phasor plot. Now, why am I saying all this? Well, because the Phasor transform is basically, it's the first element of the discrete series or the Fourier transform of this function. All the other elements carry information of the higher harmonics. The higher harmonics corresponds to doing the same operation, but instead of fitting the sine function and cosine function once, you can fit them twice or 3 times or 4 times and so on. So we have this harmonic number n stuck in here, which is telling you, okay, for n equals 1, you're fitting your trigonometric functions such that they fit exactly 1 period. What happens if you fit 2 periods in? Well, you map your distribution to a new position on the Phasor plot. So in this case, the original position is somewhere up here. And as you can see, it's shifting downwards. If you do it for n equals 3 or n equals 4, you get, what you see is that the points are kind of gradually moving to the origin. And this makes sense because as you have more and more lumps in your trigonometric function, the negative and the positive part tend to compensate each other. And at the end, say with n equals a very high number, you basically get 0 for both components. Okay, keep this in mind for the next step. Another couple of key concepts that you've heard this morning, presumably, is that if you if you assume that your decay in time is a perfect exponential, so it can be modeled perfectly as an exponential decay with a certain tau, a certain lifetime. This is the characteristic lifetime associated to that decay. You plug in this equation into these two and solve the integrals. What you find is this expression here, which you find out it is the expression of a circle in a 2D space. This is what we call a universal circle, which is telling you that any pure component, pure exponential, is always going to be on this circle. In fact, if it's a short lifetime, so if tau is small, you're kind of going to be on the right side. If it's a high number, so a long pure exponential, you're going to be on the left side. And then anything that is inside is going to be a combination of these. So this guy here could be a combination of 2, 1 on the other side, or a combination of 3 or 4, however many. So whenever you're inside, which is in general, it's always the case, you're always inside the universal circle. It's because you have combinations of lifetimes there. And then the next key point is that Phasor addition follows linear algebra, meaning that if you have a point in the Phasor space that is a contribution of 2 pure components, if the contribution is equal of the 2 components, that point has to be exactly in the middle of the position of the 2 components. So in this case, 1/2 of the G component of the first component plus 1/2 of the G component of the second component has to lead to the G component of the combination of the 2, and the same for the S. So these 2 equations would basically tell you it's basically a weighted sum. In this case, it's a perfect mean, but you're saying, well, it's half of the vector of one plus half of the vector of the other one that add up to your position on the Phasor space. And this holds for any proportion. So you have 1/4 of the long lifetime component and 3/4 of the short lifetime, you're going to be closer to the short lifetime, and the opposite holds as well. So basically, we have linear algebra that govern these vectors, and yeah, and the weights. Okay, let me plug in, running low on battery. Yeah, and the last thing is that these weights have to add up to unity. Okay, here comes, yeah. So you made a common problem that you find is that you have some data that you have measured. Your data is the capital GNS, so it's a point inside the Phasor plot. That's what you're obtaining from your microscope, and you know that your data has certain components that it should lie on the universal circle. The question is, these pixels that I'm measuring, how many of the photons that arrive belong to one component, how many belong to the other? So this is what we say, finding the weights of the pure components. So for the 2-component problem, you have some data, the 2 equations that we wrote before, saying that the sum of the G is weighted by however, what is the fraction of each of the 2 components should give you the G of your measured data. The same applies for the S, and you know that the fractions should add up to unity. So if you're getting 1,000 photons in this point here, and you're getting 900 from the guy on the left, you need to be getting exactly 100 from the guy on the right. If it's a 2-component problem, that is. So in this case, we have 3 equations, 2 unknowns. I repeat that the capital G's, we know this is what we obtained from our experiment, and the positions of the pure components, so the S and G in lowercase, we know as well. What we're trying to find is solve for the omegas, the weights or the fractions. So again, 3 equations, 2 unknowns, over determined system, we have a solution. For a 3-component problem, we still have a solution because we have 3 equations. So this is an exact solution. You have 3 unknowns, which are the 3 weights, and all the rest, you know, you can solve for it, these cases here. So this has been done in the literature for the longest time. Now, what happens if you have 4 components? Well, in 4 components, you have an indeterminate system because you only have 3 equations and 4 unknowns. You cannot solve this. There's an infinite, or from 0 to infinite solutions to this problem. Now, here comes what I was mentioning before, the higher harmonics. What if we can add a new harmonic to our information? So if all the pure components, which are the red points on the universal circle, shift to the new harmonic, and if you can measure your data with a higher harmonic, then the equations that you obtain are, you have the original equations that you had up here, plus a second set of equations for the second harmonic. Now you may think, well, is this actually new information? Or, I mean, could not be that this polygon here is the same, so the red polygon is the same as the green polygon, and therefore it's all shifted, but it's actually just these equations are just proportional to one another. And although that's what I thought at the beginning when we were discussing this with Enrico as well, it is not the case due to the non-linearity of the lifetime components on the phasor space. So it is actually a new set of equations that allow you to solve this problem for higher number of components. This, in general, you solve it for n components, you solve it by least squares. And, oh yeah, and maybe the key point number 3 is that for pure components, you can derive the positions of the higher harmonics if you're on the universal circle. So you can kind of relate the second harmonic of the pure components to the first harmonic. Okay, so now to real data. Here's some data that we kind of prepared for this problem. It's cells labeled with several components. In this case, we measure the positions of the pure components by themselves, which are rose bengal, nuc blue, acrid orange, and ethidium bromide. And then so for each pixel, we try to solve which are the fractions of each of the 4 components. So you go at each pixel and see what you obtain. In this case, you're seeing that, so this is the original intensity image, just one snapshot. You decompose, so unmix the 4 components in each pixel, and you kind of see that clearly there's a predominance of the ethidium bromide inside. There's this here, this is an accumulation of the rose bengal in this area here. And yeah, basically kind of unmixing pixel by pixel the exact proportion at each pixel of the 4 components. Here's an example with spectral data. This is a ongoing collaboration with the team here at Uruguay. And it's basically the same problem, but in this case, it's a phasor space, the spectral phasor space. We have 4 components, and in the spectral emission, we have a single snapshot, and we're trying to unmix the 4 components. In this case, it's a nice example because you see the 3rd component, which is tagging the mitochondria. In the original image, you cannot see a single mitochondria. You go here and you start to see them appearing in this component here. And this is the mixture of the 4. Okay, and now here comes the last part of the talk, which is, so till now we know the pure components where they lie, we have our data point, and we just want to find the weights of each of the component. So I remember going to Enrico and asking, well, I mean, if we can add harmonics, can we simply, adding more and more harmonics, we should be able to solve for any number of components? And his answer was definitely not, because as we saw at the beginning, the data converges to the origin and spreads out. So the noise component is too big at some point. So the answer is no. But maybe what we can do is find the fractions, so the weights and the lifetimes of a small number of components by adding more harmonics. And the answer is yes, as we found out. So what we're saying here is, till now we're finding the weights only. Now the question is, can we do a blind analysis? So we don't even know what the pure components are in our data. So how we solve this problem? So we know that the pure components should be on the universal circle. So we have the expression of the universal circle. And we know that we can relate the higher harmonics on the universal circle as well with this formula. So for example, in a case for 3 components, each of the components has its S, its G coordinate, and its weight, right? So it's 3 unknowns for each component. 3 times 3, it's 9 unknowns. Because we have the expression of the universal circle that relates the G's to the S's, we can immediately remove all the G's. So it's actually 6 unknowns using this equation here. So that means that we need at least 3 harmonics to solve this problem, which will give us 6 + 1 equations as we saw before. And these would be the equations. So it's the expression of the G's for the first harmonic, S for the first harmonic, the G and S for the second, and the G and S for the third. And you know that the weights add up to unity. So the problem is solving these equations here for all the unknowns, which are all the omegas and all the S's and G's. The way to solve this in general is to kind of put everything on one side of the equation. So grab the terms on the right, move them to the left. square it and sum it all up. And you come up with what I express down here. This d distance is the sum of all those equations into one. So you see that this is the left term of the top equation, and this is the right term of the top equation. Subtract them, square them, sum them to the second, third, and fourth. You have all the equations here. And now this distance that is a function of all your unknowns is some surface on some n-dimensional space. In this case, I'm showing in a two-dimensional space your distance of x and y, x and xy and x1 and x2. But for example, in the case that you have 6 unknowns, what you have is a distance that depends on a 6-dimensional space beneath. So at each point in the 6-dimensional space, you have some surface, some height. And the problem is minimize this surface so that the only points that satisfy all the equations are the points that make this distance equal 0. So this becomes a minimization problem, and what you have to do is start at random at some point and start shifting down till you find a point where that's the minimum of your surface. That should be the point that satisfies all those equations. As the example that I'm showing you, you can already see you tend not to have definite points. You tend to have these, what we call the valley of solutions. So that's, in general, it's not an easy problem, especially as you add up to higher harmonics. Here's actual data that we took to prove this. Again, it's the example that I showed before. Acrid orange, nuc blue, rose Bengal, 3 dyes, nuclear dyes. We measured them separately to obtain our experimental lifetime. So these are the 3 lifetimes. And then what we did is apply the system blindly so not telling the system which are the components. And what we obtained is these values here. So as you see, pretty close. 4.1 to 4.23, 2.98, 2.5. The middle one is always kind of shifting. And then the last one, 0.81 to 0.9. We published this last year, the team here at the LFD, where we showed this. I think the example that we gave was only 3 components, but we did use it for 4 components as well. And to finalize, we also applied the system on a known sample that had been used before for a previous study, in which they showed this is mouse liver, that you have mice that have a low-fat diet and mice that have what they call the Western diet. So it's a high-fat content diet. And as you can see the images, you can already tell just by eye that there's these big fat droplets here. But if you measure by lifetime, the previous paper showed that there was a long lifetime species component. And in this case, without knowing this a priori, we ran the algorithm to show that we obtained the same value of the lifetime species at around 8 nanoseconds. And we showed that there was a much higher proportion of the lifetime species in the Western diet compared to the low-fat diet. And if you map these colors to the original images, you see it's completely different one from the other. Yep, and that's about it.